In this video, we're going to be learning one of the ways that we can use an ice table, and that is to solve for the equilibrium constant. So we already know that we can calculate the value of the equilibrium constant by plugging in concentrations at equilibrium into our equilibrium expression. What an ice table allows us to do is, if we know just one of our equilibrium concentrations, we can figure out the rest. So most of the time, it is relatively easy to figure out one of your concentrations at equilibrium. We can figure out certain types of concentrations based on the pH of the solution. We can figure out certain concentrations based on the color of the solution. So there are ways to figure out the concentration of one thing, but it is usually difficult to directly measure everything. But if we know one, we can calculate the rest. So in order to solve for KEQ, we just need to know all of our initial concentrations and one equilibrium concentration. And so the general process that we're going to want to do is we'll be able to solve our ice table for the other equilibrium concentrations, or for the rest of the equilibrium concentrations. And then we can, just like we've done before, plug those concentrations in to our equilibrium expression. So let's look at a couple examples. So this is the same kind of generic example system that I used in the previous video where we were just setting up an ice table. But you'll notice we have one additional piece of information. So in the previous video, all I gave you was the initial concentrations. So we're told that we start with 2 molar A and 2 molar B. But now you are also told that at equilibrium, the concentration of A is found to be 1.8 molar. So that one piece of additional information is going to allow us to solve our ice table for the value of K. So let's set our ice table back up. We'll put our reaction at the top. Underneath it, we will have our initial, change, and equilibrium rows. Our initial concentrations were 2 molar for A and B. We had no C and no D present. C is a solid, actually, so we can just ignore this whole column. Since we have no product to begin with, we know that we're going to produce product by consuming reactant. For every 1 mole of A, we consume 2 moles of B. So when A's concentration decreases by X, B's will decrease by 2X, and we will produce X amount of D as well. So at equilibrium, we have 2 minus X molar A remaining. We have 2 minus 2X molar B, and we have X molar D. So this is exactly what we set up in the previous video. What we are told here is that our equilibrium concentration of A is 1.8 molar. So that is telling us that this is equal to 1.8. This in a different spot. So based on that extra piece of information we're given, we know that 2 minus x is equal to 1.8, so we can solve for x. We now know that x is equal to 0.2, so we can take this value of x and plug it in everywhere. The whole point of setting up ice tables the way that we do, using the coefficients here, is that x is the same everywhere. X has one value for the whole table. So once we know that x is 0.2, we can plug it in to each of these expressions. So we know that this concentration, 2 minus x, is equal to 1.8. 2 minus 2x, 2x is 2 times 0.2 is 0.4. So 2 minus 2x is going to be 1.6 molar. And then x is 0.2. So now we have concentrations for all of our species at equilibrium just by using this one to solve for the others. So at this point, we need to write our equilibrium expression and plug in our values. So if we want to write our equilibrium expression here, our product that we need to include is D. C is a solid, so it gets left out. On the reactant side, we have A, and we have B with a coefficient of 2, so that gets squared. So this is our equilibrium expression. So now we just need to plug in the values that we just calculated for our equilibrium concentrations into our equilibrium expression to calculate the value of K. So we take all of these guys and plug them in just like we did previously. So we've got A on the bottom is 1.8, B is 1.6, and that's going to get squared, and then 0.2 on the top. Once we do that out, that will give us our value of K, which comes out to about 0.043. So this last part of the process of plugging in our equilibrium concentrations should feel familiar. The only new part really is how do we get the rest of these concentrations using our ice table. So now I would like you to apply the same approach to a different problem. So down here, we have a flask is filled with 0.1 molar N2O4. It should say gas, not aqueous, sorry. And allowed to react according to the equation below. At equilibrium, the concentration of N2O4 is found to be 0.0090. Calculate the value of K. So take a couple minutes and give this one a try on your own, and then we will go through it together. So once again, we're going to want to set up and fill out an ice table first. So we'll have initial, change, and equilibrium rows. We are given our initial concentration of N2O4. N2O4 is our product, so that's going to go over there. We can assume we have no NO2 present since it's not mentioned. So in this case, we have no reactant present initially, which means that we're going to need to create some. So this is a reaction that's going to go in reverse, which means that our reactant concentrations are going to increase and our product concentrations are going to decrease as we approach equilibrium. We need to create reactant by consuming product, so the reactant concentration will go up, we'll have a positive change, product concentration will have a negative change. For every 1 mole of N2O4 that is consumed, 2 moles of NO2 will be produced. So our NO2 concentration will increase by 2x, our N2O4 concentration will decrease by 1x. At equilibrium, we started with 0 NO2 in our system and we increased that by 2x. So we will have 2x molar present at equilibrium. For the N2O4, we started with 0.1 and we used up x. So 0.1 minus x is what will remain at equilibrium. So now we are told that at equilibrium, we have 0.0090 molar N2O4 remaining. So that is telling us the value of this expression. So that tells us that .1 minus x is equal to 0.009, which means that x is equal to 0.091. So if we take this value and plug it back in to find our other concentration, that means that 2x is going to be equal to 0.182 molar. We were told this one was 0.0090. So we now have our equilibrium concentrations for everything, and we just need to plug those into our equilibrium expression and solve. So writing our equilibrium expression, we'll have products on the top. So we have N2O4 on top, and then our reactant goes on the bottom, which is NO2, and that has a coefficient of 2, so it gets squared. When we plug in our values, we will have 0.0090 divided by 0.182 squared. Don't forget your exponents when you go to do these calculations. So that comes out to be about 0.272 for our final answer here.